Okay, we're looking at atomic absorption spectroscopy, which is a very big player in the world of spectroscopy, and it was invented by an Australian scientist actually, and it's revolutionised the way that detection of metals in various environments is done. Okay, as the slide says, it's one of the most widely used instrumental techniques, and it was an Australian invention which is used all around the world. It was invented by a scientist who just thought about the idea of it while he was gardening on a Sunday morning. He was from Adelaide. I think he was in his vegetable garden or something. So it's an ingenious technique. It's very versatile, and it's basically capable of detecting over 70 metal elements. And not only does it detect 70 metal elements, it's extremely sensitive, detecting concentrations of elements of parts per billion, and in some cases, parts per million, sorry, and in some cases parts per billion. Now, the idea of it is that I think it was Dr. Alan Walsh from the CSIRO, it was the name, he realised that not only will metals emit light when they're excited, as occurs in the atomic emission spectroscopy and the flame tests, which we've already had a bit of a talk about. He realised that atoms will absorb light if the energy of the light is exactly that required to promote an electron from that metal to its normal energy or its ground state to a higher level of energy. And he invented this thing on the strength of that, which is quite a marvellous idea. So this is the situation. Every element has what's called a unique absorption spectrum. Now, just as they have a unique emission spectrum, which we've already been looking at, they have similarly a unique absorption spectrum, because they're going to absorb exactly the same frequencies of light that they would emit in another situation. So every element to be analysed requires its own light source. That's the thing. Down here, you've got to have one of those, a hollow cathode lamp, for every single element that you want to test for. The filament in this lamp is made of the element being tested for, and they're about $200 to $300 each, I believe. So you'd have quite a lot of money's worth invested if you had to have 70 of those. So think about that. What's 70 times 300? 73 to 21,000, I think. $21,000 just in lamps. So there you go. So when this filament is heated with electricity, if it's plugged in, basically it will emit light of the correct wavelength for whatever is going to be vaporized and sent up through this extremely hot flame. And what happens, just in a nutshell, is you vaporize a sample, say for example you're testing for sodium in baby food. Well, you filter it all out so all the solids are out, you dissolve all the sodium into a laboratory sample, you put it through an eductor tube and you send it up through this very hot long flame, and all the little little sodium metal atoms, it forms atomic vapor, just atoms of sodium in their ground state. That's their lowest normal state, not excited state. And what they do is they absorb that light coming through, and you will get a decrease. Once you set this detector thing, this is the monochromator, which just filters out all other light except the light that you want. So you work out how many nanometers of the correct yellow light that you want from sodium, the stronger of the emission spectra that it would absorb. And you send it through this is all diagrammatic. This is not what it's like in operation. It's just a great big box, what you see in the laboratory. But that's the principle. You basically filter the light out, and then you get a reduced signal into the detector compared to no sample of baby food going up through the eductor and in through the flame at all. And therefore that's converted then into what's called an absorbance amount. Okay, that's what happens, and it's very, very ingenious. Now, I think I probably said all this now, but we'll just go over it again. So the solution of the sample to be analysed is basically sprayed into a flame where it's converted into atomic vapour, just atoms, in their ground state. That's not mentioned there. And light containing the chosen wavelength is sent through the flame from the cathode ray lamp. And atoms of the element being analysed that are present in the flame, they absorb some of that radiation because they like that particular frequency because it's theirs. It's coming from their cousins in the cathode ray lamp. So, okay, then the light beam is passed through a filter which is called a monochromator, so you're only selecting the wavelength of light that you want, a strong absorbing signal for that particular metal, which you're already aware of in advance. And its intensity is measured on the intensity of the signal is measured by an electrical detector, and the detector works backwards to work out how much of the signal was absorbed compared to when you're not running the sample through the flame at all. So that's how it works. That's how they do it, and it's extremely smart, extremely smart. And then what they do is they calibrate they work out a calibration curve. Actually, they do that before you even run the sample in, and the calibration curve has the absorbance versus the concentration of known samples of, say, sodium in sodium chloride. And once you get a few points from known concentrations, you draw yourself a calibration curve, and then that's the key. That is the key that gets you the answer, because when you run your laboratory sample in through the system and through the flame, it'll have a certain level of absorbance, and you just go chung, chung, and there is your concentration of sodium in the sample that you're testing, which of course you then have to fiddle around and work it out in terms of, you know, how much sodium is in that specific sample, then you divide it by the sodium or the mass of the actual sample of baby food that you had or whatever it was to work out the actual parts per million of sodium. We'll show you an example of that in a minute, but this is the ingenious method that they use to do it. Okay, now here's a question for you and for me. Now, a batch of oysters which is suspected of containing dangerous levels of lead. Ugh. Oysters are filter feeders, so they basically just put all the pollutions into the ocean through their systems over and over and over and over and over and over again in an effort to get their nutrients, and they collect all these pollutants along the way. So don't eat oysters unless they're from pristine environments. So following is an example of their account of their analysis. One of the oysters was removed from its shell and chopped finely in a food processor. Yum. A 1.50 gram portion, now I'm always a bit sig fig aware, that's 3 sig figs, was heated on a hot plate with 10 mils of nitric acid. This mixture was filtered and then sprayed into the flame of an atomic absorption spectrometer. A hollow cathode lamp that emitted light with a wavelength that is absorbed by lead was in place. A significant amount of light was absorbed, indicating that there was lead in the oyster. Now, to find the concentration of lead ions in the sample, the absorbance of, they're talking about the calibration curve now, the absorbance of various different solutions containing known quantities of lead ions was also measured beforehand, and the results are graphed in figure 7.14. Now, the recommended limit of lead in oysters for human consumption is 2 parts per million because it causes brain damage, all kinds of problems. Are these oysters fit to eat? Well, now, you see, here's our calibration curve, which has already been, these points have been worked out from known concentrations of lead in various simple solutions, and that graph was worked out like that. Then along comes our sample, and we've basically got, what have we got? Yeah, we got an absorbance of this level here, which you can just read off the graph, means, and that's about 9. So it looks like it's 9 parts per million, right? In the sample. That doesn't mean there's 9 parts per million in the oyster itself. We've got to work back to that. That's just the laboratory sample. Okay? And I'll show you what I mean in a minute. Now, the work solution in the book is particularly sparse, so I thought I'd do you a proper one, okay? And here it comes. Right, before you do these questions, you should work out a bit of a game plan. I always think, oh, how am I going to do this question? I just can't start rambling and hope I'll get somewhere. I've got to think about what I'm going to do. So, here it comes. There's a strategy. Now I'm going to start off, once I've thought about what I'm going to do. So this is what I'm going to do. I've got the concentration, I want the concentration of lead in the nitric acid 10 ml solution. Then I want to work out from that the mass of lead in the 10 ml, acid solution. And then from there, now I've got the mass in the 10 ml acid solution from the second box. And now I'm going to work out from that what the concentration of lead was in the oyster. So I take that mass of lead from the second box above and I divide that by the mass of the oyster. Now that's grams per gram. Grams per gram. The parts per million can be a very confusing concept. So that's grams per gram. Now, then I multiply that by 1,000,000 to get how many grams of lead would be in 1,000,000 grams, you see? It's easy to convert from gram per gram. Gram of mass of lead in grams over mass of oysters in single grams. Well, you want to know how many grams of lead there'd be in 1,000,000 grams of oysters. So you've got to multiply your answer by 1,000,000. See? Elementary, my dear Watson. Now, yeah, okay, I'm trying to labour that point there so you get that, because a lot of students get really mucked up with parts per million. Okay, that's grams per million grams, right? In the oyster, right? Yeah, and that's parts per million. Now, once you've got that, you have your little decision to make. Is it less than or equal to 2.5 parts per million? If the answer is yes, safe, but I wouldn't eat it anyway. And if it's not, no, it's not safe. Take it back and get a refund, okay? So that's my strategy. Right, now here's my actual calculation. From the calibration graph, I can say to you that the concentration of lead in the... Now that's the laboratory sample of the 10 ml of acid I'm talking about there. The acid solution was 9 parts per million, which is 9 grams of lead per million grams of the nitric acid sample. That's what that is. Okay, that's what that is. Be clear. That's just in the laboratory sample. We've got to convert that later into grams of lead per million grams in the oyster itself. You know. Okay. First of all, we need to know how many grams of lead that means that we have in the sample. Okay, in the actual sample, we've got it in ppm. That's 9 grams of lead per million grams of sample. We need to know how many actual grams of lead there are in that 10 ml sample. So we have to assume a density thing here. We have to, because we had 10 mils. Well, we need to know that in grams, because we're dealing in grams here. So I am going to assume that the nitric acid was sufficiently dilute so that its density is approximately the same as that as water. So that means I can assume that 10 millilitres equals 10 grams, right? So that's that out of the way. Now what do we do? Okay, so I'm going to need to work out the mass of lead in the 10 ml solution, and here it comes. So what is it? It's 9 over 10 to the 6 grams of lead per gram of sample, times 10 grams of sample. And I do my calculations that way, where I've got my units kind of in brackets along with the actual numbers so that I can see what I'm doing, because I can easily see now that those grams of sample cancel out in terms of the units side of it, and I've just got now grams of lead. That's what I wanted, grams of lead in the 10 ml solution. So it's 9 by 10 to the minus 5 grams of lead. Yep. Now what have I got to do? I've got to work that out in terms of grams of, all those grams of lead in the oyster divided by the actual grams of oyster itself. That's what I'm trying to do, okay? Right. So therefore the concentration of the lead in the actual oyster, yes, it's equal to 9 by 10 to the minus 5 over 1.5 grams of oyster. Now that's grams of lead per gram of oyster, but I want grams of lead per million grams of oyster. So I have to multiply that whole thing by 1,000,000 to get how many grams of lead you'd have in 1,000,000 grams of lead, of oyster, not just 1 gram of oyster, which is what that says. Okay, here it comes, I'm going to multiply by 1,000,000, and what does that get me? What is the answer? Oh, take it back, get a refund, it's not safe. Oh, get me out of here. Oh, who recommended this restaurant to me? Well, better still, just become enlightened and become a vegan like me. That's better still. And then you really won't have this problem. You don't get any lead in broccoli, let me tell you. Now, that's the book solution, and look how sparse that is. I took 2 pages to do that for you, and they took like 3 lines. So, you know, feel sorry for them, don't you? Alright, we're at the end of the road now. So what did we learn from that? We learned some very valuable lessons about how to do calculations and also what this marvellous technology is. So we'll summarise. First one, oops, what happened to that? In AAS, a hollow cathode lamp is used that emits a particular wavelength required to excite the atoms of the element being analysed, and the concentration of metal ions is determined by measuring the amount of radiation of a particular wavelength that is absorbed. So that is very, very cool, don't you think? I think so. I think it's really cool. So I hope you enjoyed my calculation because, oh, I think I turned that L into an exclamation mark. There you are. Cool. There you go. So, yeah, I hope you liked the way I did my calculation, because hopefully that will help you to work these things out. There's one important thing you've also got to know, that ppm is also equivalent to milligrams per litre. Now, that's another one you want to sock away in your little tool chest of chemistry weapons. That's really important, okay? Remember that one. That's a direct conversion of parts per million to milligrams per litre, providing you've got a density of 1 gram per mil, which is usually the case. I better stop rabbiting on here. I hope you enjoyed that, and there's plenty more to come, I think. So, see you later.